Good morning, ladies and gentlemen, also from my side. My name is Sandro Scalise, as said, and I'm heading the Satellite Networks Department within DLR Institute of Communications and Navigation. To keep it short, my department is basically the home of most research and development activities that DLR does in the area of satellite communication. So whenever you become active in this field, later or earlier, our roads will at some point cross. Good. For today, this is probably the only presentation which does not address automotive, which is certainly very important in Germany and in Bavaria especially. But since the workshop was devoted in general to mobility, I thought it would have been nice to have also one presentation addressing the railway scenario and how railway communication is evolving and what would be the role of satellite communication in that context. Before that, however, I would like to make a short detour in general and give you a very quick overview of a number of non-terrestrial network related projects that we are having at our institute. I promise it will be short, and then I will really move to the main topic of the talk, which is the railway part. So first of all, we are very pleased to lead a large project co-founded by the European Commission, which is called 5G Stardust. This is, let's say, in terms of a time scale, a bit more on the short to mid. It's not 6G, it's still 5G, but it's still dealing with satellite and terrestrial access for distributed, ubiquitous, and smart telecommunication system. The objective here is to have a lab demonstration. We are targeting technology readiness level 5 here in this project of an integrated terrestrial and non-terrestrial network system. Looking a bit farther in the future, it's a bit, let's say, the twin project of 5G Stardust. Part of the consortium is the same, is the 6G NTN project, also co-funded by the European Commission, which looks a bit farther in the future and aim at develop 3D multi-layer architecture, focusing again on the integration between terrestrial and non-terrestrial networks. If you like, the national counterpart of the previous project is a national project this time, led by Deutsche Telekom and funded by BMBF, which as you can see from the similarity of the two pictures, addresses also this so-called three-dimensional networks, in which on top of the layer on ground, we have different layers in space with satellite at different orbits. And this project, I think, complements very well the previous one and makes sure that also, let's say, at national level, we can do an impact on fostering the role of non-terrestrial networks in future 6G system. We all know there's a big initiative by BMBF concerning 6G, and this is the flagship of the NTN part in that context. Okay, back to railway. This chart prepared by a colleague show a bit different areas in which at the Institute we are working on railway communications. Train to ground, train to train, and especially train to satellite, again then back to ground, but using a satellite in between, which is going to be the focus of my talk from now onwards. So when we talk about railway applications, these are typically classified between critical, performance, and business. Critical are those applications which are considered essential for train movements and safety, or that they are mandatory due to legal obligations. Like, for instance, any type of emergency communications, voice calls, and the so-called automatic train operation, ATO, and also automatic train control. It's a bit, if you like, if you make a liaison with the aeronautic world, it's a bit the counterpart of what in aeronautic it's called also ATC. So all type of critical applications. Then we have the performance one, which are applications meant to improve the performance of railway operation, but that are not, they don't have this critical aspects, let's say. And last not least, there's a so-called business application that in general support the railway operation in general. Passenger communication is a typical example here. Of course, the list here, it's not meant to be exhaustive, it's just to give you a feeling of the three different types of application. Moreover, when we talk about railway, we have to consider a really large variety of environments with very different features. First of all, a railway line, which we could further split into high-speed or main line, urban, suburban, and regional, which are sometimes going through more remote locations. There is, of course, one place where the satellite will come into the game. Then we have, of course, station. We have the shunting yard. That's a place where the train are left, for instance, during the night. And we have also the maintenance base and deposit. Clearly, satellite is not going to be equally important in all of those scenarios. I will bring some examples later on. So when we then focus on what could SATCOM bring to these pictures, well, first of all, in the area of Internet of Things connectivity, so for instance, connect smart wayside objects. Video connectivity is also an interesting use case, monitoring of stations, for instance, in remote areas, but also CCTV cameras to be connected in case of necessity to a central control center. We might have virtual balises driven by satellite for assisting the next generation signaling schemes. Of course, passenger communications, as I mentioned already. And in general, we can think to it as a fallback solution in all those cases where the terrestrial infrastructure for any reason is damaged, or backup in case of coverage holes, or even during handover procedures. Even more extreme, in all cases where there's no trackside or terrestrial infrastructures available, then the satellite might become the primary or even in some cases only connection means. That's a picture taken from a freight railway line in Australia. It's, I think, 1,500 kilometers long with 50 trains. Each train is 2.4 kilometer long, so really long. And it's operated driverless. So you can imagine in such a scenario that it becomes hard to rely on any other form of connectivity which is not space-based. That's what is on the table in terms of application and use case for the SATCOM. Let's now have a look at what is happening in the area of standardization. The UCI started a few years ago a big project to, let's say, create the successor of GSMR. GSMR is an extension of GSM, which was developed especially for railway. It's still a 2G system, so it's still a 2G circuit switched system. And from 2030 onwards is supposed to be replaced by this new system, which is called Future Railway Mobile Communication System. Now, the standardization process behind this is pretty complicated. It involves many players. It involves the UCI, it involves ETSI, it involves 3GPP. I put in my slide all the reference document if someone is really interested to dig into those. I won't. But the key point is that this system, which is meant to be from 2030 onwards the successor of GSMR, is meant to be a key enabler for the digitalization of railway transport. And from a technical point of view, one of the main features is that there is this decoupling of strata, mainly two different strata. The transport one, which is the one most interesting for us and for the rest of the talk, which is the one providing data connectivity. And the interesting thing is that it's based on a multiple radio access technology concept. So we are really, what we will see in railway is the evolution from a 2G circuit switch system to an IP-based communication system which support quality of service, which support priority, which should also inherently support security. And this is going to be largely based on what is happening in 3GPP. That's why some of the document which define this standard are being produced by 3GPP. And that's the connection to the NTN. Now, without entering into too many detail of the functional architecture of FRMCS, you see on the left-hand side the legacy part with GSMR. You see on the bottom side many of the applications which we have mentioned before, like the automatic train operation, like the CCTV. And the interesting part is this one here, where you see that the access can be done using 3GPP compliance technology, but also non-3GPP technologies are possible. And we will see in the next slides, SATCOM belongs actually in both of those boxes. So the existing SATCOM system, they will of course fall into that part, and what is being developed or what will be upcoming in terms of future SATCOM system which are compliant to 3GPP will be under this type of radio access. More formally, FRMCS define three types of access: the terrestrial and non-terrestrial 3GPP one, which include both options. The non-3GPP type of access, which of course includes a variety of technology, including also legacy system, provided they are compatible with 5G core network. So those systems should need in any case to be able to rely on a 5G core. And then we might have wireline non-3GPP access as well. So this is basically, let's say, the framework in which non-terrestrial network based on satellite will find their path, find their way into this future railway mobile communication system. What are we doing in that context? We have quite a number of projects in which we look at specific satellite-based solution for the railway on the basis of everything which I have presented before. In a series of projects belonging to the X2Rail initiative, which aimed at developing an adaptive train-to-ground communication system. So the previous standardization process was still at the beginning when those projects started, but as you see, what was called back then ACS is very similar to the previous concept. So also there, the idea was to have a multi-bearer system. And we developed a software-defined radio prototype of the satellite part, which was successfully tested also, unfortunately, only in the lab, not yet on train. But it offered us the flexibility to, let's say, given the implementation in software, it offered us the flexibility to test, to be flexible in terms of waveforms that we test. And the other thing we are currently doing in the framework of an ongoing ESA project, which is called TRACK, is to develop a pretty comprehensive emulator of the satellite channel. Now, in general, the railway environment in terms of propagation is nasty. When you receive a phone call on the train, the first thing you say to the other person is, "Oh, sorry, I'm on a train." Because you know that connection will be bad. And this holds for terrestrial, it also holds for satellite. It was actually my very first project at DLR 20 years ago, or even more than 20 years ago, in which we first looked and did measurements on trains from a satellite to a train. To have a look at the channel. And now, 20 years later, it still looks like that's the only measurement data available, and we are retrieving that from our archive to expand it. Back then, we measure only from GEO with a DVB-S signal. You see in the rightmost picture a snapshot, which shows one of the very peculiar effects of railway, namely the fact that whenever the train undergoes this metallic structure, which is the one supposed to provide power to the train, then you will see, depending on the frequency band, potentially deep outage, which is kind of periodic in space, also in time if the speed is constant. So this is an example of how nasty this propagation channel can be. And we are now expanding this model to be able to consider also new air interfaces that appear in the meantime, especially the 5G new radio. We are extending it to different, or trying to extrapolate it to different frequency band. The measurements back then were done in Ku band. Now we would like to be able to cover from L band 1 to 2 gigahertz up to Ka 20 to 30. And with a speed up to 500 kilometers per hour. Ambitious, but we believe we can. This will be a very valuable asset. And with this type of assets that we have, we would like to proceed in further evaluating which satellite system could better fit into the FRMCS system. This is a very preliminary evaluation done by one of our project partners, which needs to be refined, but to, let's say, cut the list of potential candidates, depending on which constellation is used. 4 were considered, a GEO constellation, a MEO constellation, and 2 LEOs, one inclined and one polar. Different air interfaces and different type of terminals on the train. So one is really handled, the other one is a larger terminal placed in the train. And to let's say reduce the list of possible candidates, the first take-home message is that 5G new radio seems to perform better than the DVB-based waveform. I was not personally involved in that assessment. I assume this is probably due to the better capability to cope with mobility fading, and that geo might still play a role, but not for handheld, only if we have the possibility to have, let's say, a larger terminal on the train, which open, of course, the big discussion topic of antennas, which is also for automotive, what will come next in all the presentations, certainly a very big topic. Again, this is, let's say, an assessment that then, using our two assets, the SDR prototype and the channel emulator, we plan to further refine in the future for the years to come. So that's what I wanted to present you today, and with that I conclude my presentation, and thank you very much for your attention.